Hello there, and welcome to Simple Sleepy Science. Tonight, we drift into something that's touching you right now. The air around you. It seems simple, ordinary even. Weather begins with air. Not clouds or rain or wind, just air. The same air that fills your bedroom right now. It seems still, but it's never truly motionless. Even in the quietest room, air molecules are dancing, bouncing off each other millions of times per second. Moving, always moving. But the oxygen filling your lungs has traveled further than most people ever will. It's crossed oceans, touched mountain peaks, been breathed by whales and sequoias. The air you're breathing has stories. If this brings you calm, if you enjoy these quiet journeys through science, please like and subscribe so you don't miss more relaxing stories tomorrow. And leave a comment telling me where you're watching from and what time it is there. I love knowing we're sharing this moment together, wherever you are in the world. Now, settle in. Get comfortable. Let's explore the invisible ocean we all swim through. The breath you just took contains about 25 sextillion molecules. That's a 25 with 21 zeros after it. Each one has been somewhere before reaching you. Some were part of clouds over the Pacific last week. Others drifted through forests in the Amazon. A few might have been in the lungs of someone across the world yesterday. Air constantly mixes and moves. It doesn't belong to any one place. This endless motion is what creates weather. Air near the ground warms up from the sun heating the earth. Warm air is lighter, so it rises. As it climbs, it cools down. Cool air sinks back toward the surface. This cycle never stops. It happens over every patch of ground on the planet. Millions of these invisible currents flowing at once. But air doesn't just carry itself. It carries water. Tiny droplets so small you can't see them. These droplets evaporate from oceans, lakes, rivers, even your skin. They float in the air as vapor, invisible, waiting. When conditions are right, they gather together, form clouds, become rain. Then the cycle starts again. Air also carries heat, not just the warmth you feel, but actual thermal energy moving from place to place. The tropics get more sunlight than the poles, so air near the equator heats up and rises. It flows toward the poles high in the atmosphere. Meanwhile, cold air from the poles slides along the ground back toward the equator. This creates giant loops of circulation that wrap around the entire planet. And air carries momentum. When it moves in one direction long enough, we call it wind. That wind pushes clouds across the sky. It stirs the ocean surface into waves. It bends trees and carries seeds to new soil. Wind is just air that's decided to go somewhere. Everything we call weather is air in motion. Air carrying water, air carrying heat, air carrying itself across vast distances. The same air that surrounds you now was somewhere completely different a week ago. It will be somewhere new a week from now. You're breathing in the world. And right now, in this moment, that world has come to rest in your lungs before continuing its endless journey. All that moving air carries water upward. And when enough water gathers in one place, you get a cloud. But here's what seems impossible. Clouds are heavy, really heavy. A typical fluffy cloud, the kind you see on a summer day, weighs about 1,000,000 pounds. That's roughly 100 elephants floating above your head. So why doesn't it fall? The answer is in how that weight is spread out. 1,000,000 pounds sounds massive, but it's not packed into one solid chunk. It's divided among billions and billions of tiny water droplets. Each droplet is smaller than the width of a human hair. Some are so small that 50 of them side by side wouldn't stretch across the period at the end of this sentence. When something is that small, air can hold it up. Gravity pulls on each droplet, trying to drag it down. But air pushes back. Air molecules constantly bump into the droplet from below, giving it little upward nudges. These nudges happen millions of times per second. They're strong enough to keep the droplet floating. It's not that gravity stops working. It's that the air's push balances gravity's pull. Think of it like this. Drop a rock in water and it sinks fast. Drop a grain of sand and it sinks slower. Drop a particle of dust and it drifts down so gently you barely notice. Cloud droplets are even smaller than dust. In air, they barely fall at all. They drift, they hover, and the slightest upward breeze keeps them aloft. But there's more to it. Warm air rises, remember? Inside and beneath a cloud, there are constant updrafts, currents of warm air flowing upward. These updrafts can move faster than the droplets fall, so the droplets get carried up even as gravity tries to pull them down. They're trapped in an upward stream, like a ball balanced on a fountain of water. The ball wants to fall, but the water keeps pushing it back up. This is why clouds grow upward instead of just sitting there. The base of the cloud stays roughly at the same height. That's where the air temperature drops enough for water vapor to condense into droplets. But the top keeps building higher as updrafts carry droplets up into colder air. Some storm clouds grow so tall they reach 6 miles high, all held up by air. Eventually, the droplets inside a cloud start bumping into each other. They stick together. One droplet plus another equals a bigger droplet. This happens millions of times. The droplets grow heavy enough that air can't hold them anymore. Gravity wins. They fall. We call this rain. But until that happens, clouds just float. 100 elephants worth of water suspended in the sky by nothing but tiny collisions between air and droplets. It's a perfect balance. The cloud isn't defying physics. It's demonstrating them beautifully. Weight doesn't matter as much as we think. How that weight is distributed changes everything. And right now, above you somewhere, 1,000,000 pounds of water is floating on air. Sometimes those clouds carry something different than rain. When the air is cold enough, water skips the liquid phase entirely. It freezes, and when frozen water falls from clouds, the world changes in a way you can hear, or rather, can't hear. If you've ever been outside just before snow starts falling, you know the feeling. The world gets quiet. Not just quieter, quiet in a way that feels thick, heavy, like someone turned down the volume on everything. There's actual science behind that hush. Sound travels through air as vibrations. Molecules bump into each other, passing the vibration along like a wave. But when air is full of moisture and cold, those vibrations don't travel as well. The water molecules in the air absorb some of the sound energy. It's subtle, but your ears notice. Everything sounds muffled, distant, soft. Then the snow begins, and that's when the real silence arrives. Each snowflake has a structure unlike anything else in nature. 6-sided crystals branching out in intricate patterns. But what matters for sound is that these crystals are full of tiny air pockets. The branches create gaps, spaces, empty areas between the ice. When sound waves hit a snowflake, they bounce around inside these spaces. The energy gets trapped, absorbed. The sound doesn't pass through. One snowflake does almost nothing, but billions of them falling at once create a blanket of sound absorption dropping from the sky. As snow accumulates on the ground, it builds up in layers. More air pockets, more trapped space. Fresh snow can be up to 90% air. It's mostly emptiness held together by ice crystals. This makes snow one of nature's best soundproofing materials. Better than foam, better than fabric. The combination of the crystal structure and all that trapped air absorbs sound across almost every frequency. High notes, low rumbles, all of it gets dampened. Walk through fresh snow and listen. Your footsteps sound different, muffled, contained. The crunch happens right at your feet, but doesn't echo, doesn't carry. Traffic noise from a nearby road fades to almost nothing. Voices don't travel as far. Even wind sounds softer when it's moving through falling snow. The effect is strongest with fresh, fluffy snow, the kind that falls in cold, calm conditions. Each flake lands gently and keeps its structure. The air pockets stay intact. Over time, if snow melts slightly and refreezes, or if it gets packed down, it loses those air spaces. The sound-absorbing quality fades. Icy, compacted snow doesn't hush the world the same way. But in those first hours after snowfall, the silence is profound. It's not just the absence of sound, it's the active removal of it. Every noise gets pulled out of the air by billions of tiny ice crystals. The world feels wrapped in something soft, protected, peaceful. This is why snow at night feels especially magical. Darkness already limits what you can see, and snow limits what you can hear. Two of your main senses dimmed at once. You're left with just the quiet and the cold, and the gentle accumulation of frozen water erasing the noise of the world. The silence before snow is anticipation. The silence during snow is transformation, and both are written into the physics of ice and air. Snow falls when the air is cold enough, but rain is different, or so it seems. Here's something that feels wrong, but isn't. Every raindrop that hits your skin in the middle of summer started as ice. Every single one. Rain doesn't begin in the warm, grey clouds you see on rainy days. It begins much higher, up where the air is thin and freezing. Even when the ground is hot and humid, the upper atmosphere is always cold. Several miles up, temperatures drop below freezing, no matter what season it is. That's where raindrops are born. As ice, water vapor rises through the atmosphere, higher and higher. Eventually, it reaches air cold enough to freeze it. But water needs something to freeze onto. It can't just become ice out of nowhere. It needs a surface, a starting point. That's where dust comes in. Tiny particles of dust float in the upper atmosphere. Some are blown up from deserts. Some are ash from volcanoes. Some are even particles from space, debris from meteors that burned up entering Earth's atmosphere. These specks are smaller than you can see, but they're everywhere, and water vapor loves them. When vapor touches one of these dust particles in cold air, it freezes around it instantly. The particle becomes the core of an ice crystal. More vapor freezes onto the crystal. It grows, gets heavier, starts to fall. As it falls, it bumps into other ice crystals. They stick together. The crystal becomes a clump. The clump becomes heavier still. Gravity pulls it down faster, but it's still ice, still frozen solid. Then something happens on the way down. The air gets warmer. The ice crystal passes through layers of atmosphere that are above freezing. The outer edges start to melt. The crystal becomes a droplet with an icy core. Then the core melts too. Now it's entirely liquid, a raindrop. By the time it reaches the ground, all trace of ice is gone. It's just water, warm water even. But minutes ago, miles above your head, it was a tiny frozen crystal built around a speck of dust. This happens with every raindrop in every rainstorm, even in the tropics, even in the heat of summer. The clouds you see might be warm, but above them, where the rain actually forms, it's always freezing. Rain is just melted snow that never made it to the ground as snow. Sometimes, the air below the cloud is so dry or so warm that raindrops evaporate before they hit the ground. You can see this from a distance. Dark streaks falling from a cloud, but fading away before they reach Earth. It's called virga, rain that never lands. Those drops were ice too, formed in the cold, melted on the way down, then vanished back into vapor. But when conditions are right, when there's enough moisture and the air below is cool enough, the drops survive their fall. They hit leaves, puddles, your skin, and each one is the end of a journey that started as ice wrapped around ancient dust. Summer rain is winter's ghost, frozen water that found its way back to liquid just in time to fall. The next time rain touches your face, remember, seconds ago it was ice. Rain falls because gravity pulls it down, but before it falls, wind carries the clouds that hold it. And wind isn't the chaotic force it seems to be. It follows rules, patterns, invisible highways carved into the sky by simple physics. Wind is just air moving from one place to another. But why does it move? The answer is difference. Temperature difference, pressure difference. Wherever there's inequality in the atmosphere, air flows to balance it out. Start with the sun. It doesn't heat the Earth evenly. The equator gets direct sunlight. The poles get angled rays that spread out over more surface area. So the equator is hot and the poles are cold. This difference drives everything. Hot air at the equator rises. It has to go somewhere, so it flows toward the poles high in the atmosphere. Meanwhile, cold air at the poles is heavy. It sinks and slides along the ground back toward the equator. If Earth didn't spin, you'd have two simple loops, one in each hemisphere. North and south circulation, clean and straightforward. But Earth does spin, and that changes everything. As air moves north or south, the ground beneath it is rotating. The equator moves faster than the poles because it has more distance to cover in the same 24 hours. Air moving away from the equator carries that faster rotation with it. When it reaches slower rotating areas, it's moving faster than the ground below. This curves its path. Air heading toward the pole bends east. Air heading toward the equator bends west. This is called the Coriolis effect. It's not a force pushing the air. It's just the consequence of movement on a spinning sphere. But it creates predictable patterns. The simple pole to equator loops break into smaller cells. 3 in each hemisphere. Each cell circulates air at different latitudes. And between these cells, boundaries form where air flows strongly in one direction. These are the jet streams, the trade winds, the westerlies. These aren't random gusts. They're steady rivers of air that flow year-round. Ancient sailors knew about them. They planned routes around these wind patterns. Ships crossed oceans by following the reliable paths of moving air. The wind touching your face right now is part of this system. It might have come from hundreds of miles away, following one of these atmospheric highways, pushed by temperature differences, curved by Earth's rotation, guided by the landscape below. Mountains change wind, patterns too. Air flowing toward a mountain has to rise. As it climbs, it cools. Cool air can't hold as much moisture, so the wind drops its water as rain on one side of the mountain. The other side stays dry. This is why you can have rainforest on one slope and desert on the other. Same mountain, different sides, all because of wind. Coastlines create their own wind patterns. During the day, land heats up faster than water. Hot air over land rises. Cool air from the ocean rushes in to replace it. That's a sea breeze. At night, it reverses. The land cools faster. Air over the water is now warmer. It rises and pulls air from the land out to sea. None of this is random. Wind flows according to temperature, pressure, rotation, and terrain. It follows paths determined by physics. The atmosphere has structure, order, and the wind knows exactly where it's going. Wind carries water vapor across landscapes. Sometimes that vapor condenses high in the sky. We call that a cloud, but sometimes it condenses right where you're standing. We call that fog. They're the same thing, the only difference is altitude. A cloud is just water droplets or ice crystals suspended in air. Fog is also water droplets suspended in air. Same size droplets, same physics, same appearance. If you could lift fog 1,000 feet up, it would look exactly like a low cloud. If you could pull a cloud down to ground level, it would be fog. The difference is where they form. Clouds form when warm, moist air rises and cools. Fog forms when cool air meets warm, moist ground, or when warm, moist air meets a cold surface. Either way, the air temperature drops to the point where it can't hold all its moisture anymore. Water condenses. Droplets appear. Suddenly, you're standing inside what would normally be floating above you. There are different ways this happens. Sometimes, on a clear night, the ground radiates heat away into space. It cools down fast. Air touching the cold ground cools too. If that air has enough moisture, fog forms right at the surface. This is radiation fog. It usually happens in valleys where cool air settles and can't escape. Other times, warm air blows across cold ground or cold water. The air cools from below. Again, if it's moist enough, fog appears. This is advection fog. It's common near coastlines, where warm land air drifts out over cold ocean water. The fog can be thick and last for days. When rain falls through cold air, it can evaporate and add moisture to that cold air. If enough moisture builds up, the air becomes saturated, can't hold anymore. Fog forms even while rain is still falling. This is precipitation fog. It feels strange to be in rain and fog at the same time, but it happens. Fog doesn't have the same structure as a cloud up high. There are no strong updrafts holding it together. It just sits there, dense and still, until something disturbs it. Wind can push it around or tear it apart. Sunlight can warm the air enough to evaporate the droplets. The ground heating up does the same thing. That's why morning fog often burns off by midday. Walking through fog is walking through a cloud. The droplets are so small that you barely get wet. They float around you, stick to your hair and clothes in tiny beads. Everything beyond a few feet fades into whiteness. Sound behaves differently, absorbed by all that suspended water. Distance becomes meaningless. You lose perspective. Fog is proof that the sky and ground aren't separate realms. The same processes happen at any altitude. Water condenses when air can't hold it anymore. Whether that's a mile up or right at your feet doesn't matter to physics. The atmosphere touches the earth. Sometimes it's clear where one ends and the other begins. Sometimes, on foggy mornings, the boundary disappears completely. You stand in a cloud, breathe it, move through it, and for a little while, the sky comes down to meet you where you are. Fog is calm, gentle, but weather has a violent side too, and nothing demonstrates that power quite like lightning. It looks instant, a sudden flash connecting cloud to ground. But that flash is the end of a process that takes time. Milliseconds, sure, but lightning isn't as instantaneous as it seems. Inside a thunderstorm, ice particles and water droplets collide constantly. These collisions create static electricity, the same force that makes your hair stand up when you rub a balloon on it. Lighter ice crystals get pushed to the top of the cloud. They carry a positive charge. Heavier particles sink to the bottom. They carry a negative charge. The cloud becomes a giant battery. Positive on top, negative on bottom. That negative charge at the cloud's base is strong, really strong. It creates an electric field so powerful that it starts ionizing the air below, stripping electrons off air molecules. This creates a channel of charged particles, a path. This channel reaches down from the cloud in steps. Each step is about 50 yards long. The channel branches as it goes, searching for the easiest route to the ground. This is called a stepped leader. It's invisible to the human eye, too dim. It moves fast, but not instantly. It zigzags down at about 200 miles per second. That sounds quick, but it takes several milliseconds to cover the distance from cloud to ground. During this time, nothing bright happens. the channel is just quietly building a bridge through the air. Meanwhile, the ground responds. The negative charge approaching from above pushes electrons in the ground away. This creates a positive charge on anything sticking up. Trees, buildings, people standing in open fields. Positive charges send up their own channels called streamers. They reach upward, trying to meet the leader coming down. When the downward leader and an upward streamer connect, the circuit completes. Now, there's a conductive path from cloud to ground, and that's when the bright flash happens. Electrons flood down through the channel. This is called the return stroke. It moves at about 1/3 the speed of light. The air in the channel heats up to 50,000 degrees, hotter than the surface of the sun. That extreme heat makes the air glow white. That's the flash you see. But the electrons are actually flowing from ground to cloud, not cloud to ground. The return stroke shoots upward. Your eyes can't separate the stepped leader from the return stroke. They happen too close together in time. You just see one bright bolt. But cameras can catch the difference. Slow motion footage shows the channel building down, then the bright flash racing back up. And it doesn't stop there. Often, after the first return stroke, the channel stays ionized for a moment. More charge flows down from the cloud. Another return stroke fires back up. This can happen several times in a fraction of a second. That's why lightning seems to flicker. Each flicker is another stroke using the same channel. Thunder comes from the same superheated air. When the channel heats up so fast, the air expands explosively. That expansion creates a shockwave. Sound. The boom travels at the speed of sound, much slower than light. So, you see the flash first. Then, you hear the thunder. Count the seconds between them. Each 5 seconds equals about 1 mile of distance. Lightning might seem instant, but it's a negotiation between cloud and earth. A slow dance at high speed. Lightning flashes white, but it contains every color. The same is true for sunlight. White light is actually a mix of all colors combined. And when that sunlight passes through the atmosphere, it splits apart. We see some of it, but not all. The sky above you right now is full of colors your eyes can't detect. You see blue on a clear day. That's real, but it's just a fraction of what's actually there. Sunlight contains wavelengths beyond the visible spectrum. Ultraviolet at one end, infrared at the other. Your eyes simply weren't built to register them. Blue sky happens because of scattering. Sunlight hits molecules in the atmosphere. Nitrogen, oxygen. These molecules are tiny compared to most wavelengths of light, but they're just the right size to scatter blue light more than other colors. Blue bounces around the sky in all directions. That's why the whole sky looks blue instead of just the path of direct sunlight. But shorter wavelengths than blue get scattered even more. Violet scatters more intensely than blue. So, why isn't the sky violet? 2 reasons. First, the sun produces less violet light than blue. Second, your eyes are less sensitive to violet. The blue overwhelms it, but the violet is there. You just can't see it clearly. Beyond violet lies ultraviolet. UV light. It's invisible to you, but very much present. It scatters through the sky just like visible light, more intensely even. Some animals can see it. Bees see ultraviolet patterns on flowers that guide them to nectar. Birds use UV light to navigate. To them, the sky looks different than it does to you, richer, more complex. On the other side of the spectrum is infrared, wavelengths longer than red. You can't see infrared, but you can feel it. It's heat. The sun bathes the earth in infrared radiation constantly. It warms your skin, heats the ground, drives all the temperature differences that create weather. Infrared is everywhere in the sky. You just experience it as warmth instead of color. The atmosphere treats different wavelengths differently. It's transparent to some, opaque to others. Visible light passes through easily. That's why you can see the sun and stars. But the atmosphere absorbs most ultraviolet before it reaches the ground. Good thing too. Too much UV damages living tissue. The ozone layer up in the stratosphere blocks the most dangerous wavelengths. What gets through is enough to tan your skin, but not enough to cook you. Infrared gets partially absorbed by water vapor and carbon dioxide. These gases trap heat. That's why cloudy nights stay warmer than clear ones. The clouds absorb and re-radiate infrared back to the ground. Clear skies let it escape into space. At sunset, the sky turns red and orange. That's because sunlight travels through more atmosphere when the sun is low. Blue light gets scattered away. What's left are the longer wavelengths: red, orange, yellow. But even then, infrared and ultraviolet are present. Invisible, but there. The sky is broadcasting in frequencies you'll never perceive. Your eyes are limited instruments. They capture a narrow slice of reality. The full spectrum of light filling the air around you is far richer than the blue you see. The sky has colors beyond color, and they're shining on you right now. Light comes in infinite wavelengths, and frozen water comes in infinite forms. You've probably heard that no two snowflakes are alike. It sounds too perfect to be true, like a nice story we tell children. But it's not a story. It's mathematics and chaos working together. A snowflake begins as a tiny ice crystal around a dust particle high in a cloud. Water molecules freeze onto it one at a time. Each molecule has to fit into the crystal structure. Ice naturally forms hexagons because of how water molecules bond. 6 sides, 6 points. That's why snowflakes have 6-fold symmetry. But here's where it gets complicated. As the crystal falls through the cloud, it encounters different conditions. Temperature changes, humidity changes, air pressure varies. Each of these factors affects how water molecules attach to the growing crystal. Warmer air makes crystals grow in plates, flat hexagons. Colder air makes them grow as columns, tall, narrow shapes. Really cold air creates simple prisms. Medium cold air creates intricate branching patterns. And the crystal keeps falling, keeps passing through layers of different conditions. Each layer adds growth in a slightly different way. The crystal tumbles as it falls, but all 6 arms are exposed to roughly the same conditions at the same time. So they grow in similar ways. That's why snowflakes are symmetrical. The 6 branches mirror each other because they all experienced the same journey. But no 2 snowflakes take exactly the same path. One might drift left while falling, another might tumble faster. One passes through a pocket of very humid air. Another misses that pocket by inches. Every tiny variation in the path creates tiny differences in how the crystal grows. Temperature matters too. At 15 degrees, crystals grow into thin plates. At 5 degrees, they form hollow columns. At 0 degrees, they create fern-like dendrites with elaborate branches. A snowflake might start growing at 15 degrees, then fall into air that's 5 degrees, then 0. Each temperature adds a different structure onto what was already there. The result is a history of the fall written in ice. There are more possible ways for a snowflake to form than there are atoms in the universe. The variables are endless. Temperature, humidity, pressure, time spent in each layer, path through the cloud, speed of falling, amount of supercooled water encountered. Each factor has countless possible values. Multiply them all together and you get astronomical numbers. Simple snowflakes do look similar. The tiny crystals that form in very cold, dry air are basic prisms or plates. Under a microscope, they're hard to tell apart, but the big, elaborate snowflakes, the ones with intricate branching, those are unique. The complexity grows with the variety of conditions encountered. When snowflakes melt and refreeze, they lose their structure. They become granular ice, smooth, simple. The intricate patterns disappear. But fresh snowflakes caught on a dark surface show their geometry clearly. 6 sides, 6 branches, each branch reflecting the exact atmospheric conditions it grew through. Every snowflake is a tiny frozen record of a journey, a piece of ice that documented every change in temperature and moisture it experienced. Not magic, just physics creating infinite variation. The uniqueness isn't special treatment. It's the inevitable result of complexity meeting randomness. And they fall by the billions, each one different, each one a small crystal miracle that melts in your hand. Snowflakes are unique to their path through the air. Rainbows are unique to your position on the ground. Move a few feet and you see a different rainbow. The one you're looking at exists only for you. A rainbow isn't a physical object hanging in the sky. It's an optical effect. Light and water and geometry working together. And your eyes are part of the equation. You're not just observing a rainbow, you're completing it. Here's how it works. Sunlight hits raindrops in the air. Each drop acts like a tiny prism. Light enters the drop, slows down, bends. Different wavelengths bend at different angles. Red bends least. Violet bends most. The light bounces off the back of the drop, then exits the front, separated into colors. But you only see a rainbow when the angle is right. The light has to leave the drop at about 42 degrees from the line between the sun and your eye. That's the magic angle. Any drop at that angle produces visible color. Drops at other angles send their light somewhere else, maybe to someone standing next to you, but not to your eyes. This means the rainbow you see is made of specific drops. Drops arranged in an arc at exactly 42 degrees from your viewing angle. Someone standing 10 feet away sees a rainbow made of completely different drops. Their angle is different. Their drops are different. Their rainbow is different. the rainbow is always opposite the sun. If the sun is behind you and low in the sky, the rainbow is in front of you and high. If the sun is to your left, the rainbow is to your right. You're always at the center of your own personal rainbow. It moves with you. You can't get closer to it because it's defined by your position. And rainbows are actually full circles. You just can't see the bottom half from the ground. The earth gets in the way. But from an airplane, you can see the complete circle. A rainbow wrapping all the way around. Some pilots see them regularly. The shadow of the plane sits right in the center of the circular rainbow. You and your shadow are always at the center of your rainbow, whether you can see it or not. Sometimes you see a double rainbow. The second arc is dimmer and the colors are reversed. Red on the inside, violet on the outside. This happens when light bounces twice inside the raindrop instead of once. That extra bounce flips the color order and takes more energy. So the second rainbow is always fainter. Between the two rainbows is a darker band. This is called Alexander's band. It's the area where no refracted light reaches your eyes. The light gets scattered in other directions. So the sky looks darker there compared to the bright arcs on either side. Rainbows need three things: sun, rain, and you standing in the right spot. Take away any of those, and the rainbow disappears. The water droplets are still there. The sun is still shining. But without your eyes in the correct geometric relationship to both, there's no rainbow. Every rainbow is personal, made of light meant only for your eyes, created by drops positioned perfectly for your view, defined by where you stand and where the sun sits behind you. It's not permanent, it's not solid. It's a moment of geometry that exists because you're there to see it. Rainbows come from water suspended in air, but most of the time you can't see that water. It's there anyway. Every breath you take contains it. On humid days, you're breathing in thousands of water molecules with every inhale. Invisible weight floating all around you. Humidity is water in gas form. Water vapor. The molecules have evaporated from oceans, lakes, rivers, soil, plants, even your skin. They spread through the air like any other gas, mixing with nitrogen and oxygen. Completely transparent. You can't see them, can't smell them, but your body knows they're there. Air can only hold so much water vapor. The warmer the air, the more it can hold. Cold air has less room for moisture. That's why cold air feels dry and warm air feels humid. It's not that cold air pushes water out. It's that cold air simply can't contain as much. When air holds all the water it can, we call that 100% humidity. Saturated. Any more moisture and it starts condensing into liquid. That's when you get dew, or fog, or clouds. The air gives up water because it can't carry it anymore. But here's what matters for how you feel. Sweat. Your body cools itself by sweating. The moisture evaporates from your skin and takes heat with it. That's the whole point. Evaporation equals cooling. But evaporation only works if the air around you can accept more water vapor. On a dry day, sweat evaporates easily. The air is thirsty. It pulls moisture off your skin fast. You cool down efficiently. Even if it's hot outside, you feel okay because the cooling system works. On a humid day, the air is already full of water vapor. It can't take much more. Your sweat just sits on your skin, doesn't evaporate, doesn't cool you. You feel miserable even if the temperature isn't that high. That's why weather reports mention heat index. It combines temperature and humidity to show how hot it actually feels. 90 degrees with low humidity feels warm but manageable. 90 degrees with high humidity feels dangerous. Your body can overheat because sweat stops working. Humid air is also literally heavier than dry air. Water vapor molecules are lighter than nitrogen or oxygen molecules. But there are so many of them added to the mix that the total weight increases. The air presses down on you with more force. You feel it as thickness, heaviness, like the air has substance. This invisible moisture is what powers weather. All those water molecules floating around eventually gather into clouds. The clouds grow heavy and release rain. The rain soaks the ground. Then it evaporates back into the air. The cycle continues forever. Humidity is just one stage in that cycle, the invisible stage, the stage where water hides in plain sight. Walk outside on a muggy summer evening, and you're walking through water. Not liquid water, not solid ice, but water nonetheless. It surrounds you, enters your lungs, sticks to your skin. The air isn't empty, it's full of moisture that came from somewhere else and is heading somewhere new. You're breathing the ocean, breathing the forest, breathing every lake and river that contributed molecules to the atmosphere. Invisible water, everywhere, waiting to become visible again. Humidity is water molecules moving through air. Temperature is those same molecules moving faster or slower. Heat isn't a substance, it's motion. The warmth you feel on a summer day is actually billions of molecules vibrating at high speed. Everything is made of atoms and molecules. They're never completely still. Even in solid objects, they vibrate in place. In liquids, they slide past each other. In gases like air, they fly around freely, bouncing off each other millions of times per second. This constant motion is what temperature measures. When something is hot, its molecules are moving fast. When something is cold, they're moving slower. That's all temperature is. Average molecular speed. A thermometer doesn't measure heat directly. It measures how fast molecules are jiggling. On a hot day, air molecules zoom around at about 1,000 miles per hour, faster than the speed of sound. They collide with everything. Your skin, the walls, each other. Each collision transfers a tiny bit of energy. That's what you feel as heat. The accumulated impact of trillions of high-speed molecular collisions every second. On a cold day, those same molecules slow down. Maybe 700 miles per hour. Still incredibly fast by human standards, but slower than before. Fewer collisions per second. Less energy transferred. You feel cold, not because something called cold is entering your body, but because heat is leaving it faster than usual. The slow-moving air molecules can't replace the warmth your body radiates away. This is why metal feels colder than wood at the same temperature. Metal conducts heat better. It pulls warmth from your skin faster. Wood is a poor conductor. It takes heat away slowly. But both are the same temperature. Your perception of cold is really about how quickly you lose heat, not the actual temperature of the object. Water has a special relationship with temperature. It takes a lot of energy to heat water up or cool it down. Water molecules cling to each other through hydrogen bonds. These bonds have to be broken for the molecules to move faster. So, water resists temperature change. This is why oceans moderate climate. They absorb huge amounts of heat in summer without warming up much. They release that heat slowly in winter. Coastal areas stay more stable because water buffers the extremes. Ice is water molecules locked in a rigid structure. They still vibrate, but they can't move freely. All that motion is trapped. Add heat, and the vibrations increase until the bonds break. The ice melts. The molecules can flow past each other now. Add more heat, and they vibrate so violently, they break free completely. The water boils. The molecules fly apart into steam. Steam molecules at boiling temperature move about the same speed as air molecules on a scorching summer day. But steam feels much hotter because water molecules are heavier. They carry more energy per collision. That's why steam burns are so dangerous. Each molecule hitting your skin delivers a powerful punch of thermal energy. Temperature is everywhere. In the air around you, in your body, in the ground beneath your feet. It's not hiding in objects. It is the objects. Everything is dancing at the atomic level. The faster the dance, the hotter it feels. Warmth is motion. You can feel, but never see. The invisible vibration of reality itself. Temperature is molecular motion. Your body creates its own heat through that same motion. Cells burning energy, molecules vibrating. And your body works constantly to keep that heat from escaping too fast. Wind makes that job harder. Your skin radiates heat into the air around it. This creates a thin layer of warm air clinging to your body, maybe a 1/4 inch thick. This layer acts like insulation, a personal microclimate. The air right next to you is warmer than the air a foot away. As long as that warm layer stays in place, you lose heat slowly. You feel comfortable. Wind strips that layer away. Fresh, cold air rushes in, makes contact with your skin, steals heat, then gets pushed away by more wind. More cold air arrives, takes more heat. The cycle repeats continuously. Your body keeps warming the air, and wind keeps replacing it with colder air. You lose heat much faster than you would in still conditions. The actual air temperature hasn't changed. A thermometer in the wind reads the same as one sheltered from it. But your body tells you something different. It feels colder. This is wind chill. Not a real temperature drop, but a real increase in heat loss. Weather forecasts give wind chill numbers to show how cold it feels. These numbers are calculated based on wind speed and actual temperature. They estimate how quickly exposed skin loses heat. At 20 degrees with no wind, you might feel fine for a while. At 20 degrees with 20 mile/hour wind, frostbite can start in 30 minutes. Same air temperature, different heat loss rate. Water makes wind chill worse. Wet skin loses heat much faster than dry skin. Water conducts heat away from your body more efficiently than air does. So, if you're wet and standing in wind, you're losing heat through two mechanisms. Evaporation and convection. The wind evaporates the water, which pulls heat away, and it blows away the warm air, which pulls more heat away. Combined, they can drop your core temperature dangerously fast. This is why swimmers get cold so quickly, even in mild weather. Water surrounds them, touches every inch of skin, pulls heat away continuously. Moving water or waves make it worse by constantly bringing fresh cold water into contact with the body. It's like wind, but more efficient. Your body fights back by constricting blood vessels near the skin. Less blood flow means less heat reaches the surface to be lost. Your extremities get cold first. Fingers, toes, nose, ears. The body sacrifices them to protect the core. If you start shivering, that's your muscles generating extra heat through motion. Rapid, involuntary contractions burning energy to stay warm. Buildings block wind. That's part of their purpose. Inside, you have your warm air layer, and nothing disturbs it. You lose heat only through radiation, which is slow. Outside in wind, you lose it through convection, which is fast. 4 walls and a roof keep the moving air away from you. Wind doesn't change the temperature, but it changes your experience of that temperature completely. The colder the air and the faster the wind, the quicker you lose heat. Wind chill is your body's honest report of thermal stress. The air might be 30 degrees, but to your skin, fighting to keep its warm layer intact, it feels like 10. And that difference can be the difference between comfort and danger. Wind affects how you feel because you live at the bottom of the atmosphere, all that air stacked above you. But here's something that changes how you think about weather. That stack isn't nearly as tall as it seems. The atmosphere is thin, remarkably thin. If you could shrink Earth down to the size of an apple, the atmosphere would be thinner than the skin. All the air that makes weather, that you breathe, that creates clouds and wind and rain, exists in a layer about as thick as the paint on a globe. That's it. A delicate shell wrapped around rock. Most people imagine the atmosphere extending far into space, fading gradually over hundreds of miles. But that's not how it works. Air has weight. Gravity pulls it down, so most of it packs into the lowest layer. About 80% of the atmosphere's mass sits below 10 miles altitude. Commercial jets fly at 7 miles up. They're already above most of the air. Go to the top of a tall mountain and you notice the difference. Less air above you means lower pressure. Lower pressure means less oxygen per breath. Your body has to work harder. Climbers on Mount Everest are at the edge of breathable atmosphere. Above 26,000 feet, there's not enough oxygen to sustain human life for long. The death zone, and that's only 5.5 miles up. The layer where weather happens is even thinner. It's called the troposphere. From the ground to about 7 miles up at the poles, 12 miles at the equator. Everything you think of as weather exists in this narrow band. All clouds except the very highest. All rain, all snow, all storms. The troposphere is where temperature drops as you go higher, where warm air rises and cold air sinks, where moisture condenses and falls. Above that is the stratosphere. Calm, stable. Temperature actually increases with altitude there because of the ozone layer absorbing ultraviolet light. No weather, no turbulence, just thin, cold, quiet air. Airplanes sometimes climb into the lower stratosphere for a smoother ride. They leave the weather behind. Higher still, the air gets so thin it barely qualifies as air anymore. Individual molecules spread far apart. The boundary between atmosphere and space isn't sharp, it's gradual. But by about 60 miles up, there's essentially nothing left. Satellites orbit above that. They encounter almost no air resistance, no drag, just the occasional stray molecule. Earth's atmosphere exists because gravity holds it down. But gravity weakens with distance. Lighter molecules like hydrogen and helium escape from the upper atmosphere into space. Heavier molecules like nitrogen and oxygen stay trapped. Over billions of years, Earth has lost some atmosphere this way. Not much, but some. The atmosphere is slowly leaking. Other planets have different atmospheres. Mars has one that's thin even at the surface. About 1% of Earth's pressure. Venus has a crushingly thick atmosphere, 90 times Earth's pressure, made mostly of carbon dioxide, hot enough to melt lead. Each planet's atmosphere depends on its size, temperature, and distance from the Sun. But here on Earth, we have this paper-thin layer of air, just enough to breathe, just enough to create weather, just enough to scatter light and paint the sky blue. All of weather, all of climate, every storm and breeze happens in a shell so thin it would barely show up on a scale model. We live at the bottom of a shallow ocean of air. And that's where all the magic happens. Weather happens in a thin shell of atmosphere. But some weather happens right at the surface, so close to the ground you can touch it with your hand. Dew appears overnight on grass and leaves. Most people assume it falls like gentle rain. It doesn't. It forms right where you find it. Dew is water pulled directly from the air, not from clouds, not from fog, from the invisible moisture floating in the air that touches the ground. The same humidity we talked about earlier. At night, the process of condensation happens at ground level. Here's how it works. After sunset, the ground loses heat. All day, the Earth absorbs sunlight. At night, with no sun, that heat radiates back into space. The surface cools down. Grass cools. Leaves cool. Metal surfaces cool. Anything exposed to the open sky drops in temperature. Air touching these cool surfaces cools too. And cool air can't hold as much water vapor as warm air. The moisture has to go somewhere, so it condenses. Water vapor becomes liquid water. Tiny droplets appear on whatever surface the air is touching. That's dew. The temperature at which this happens is called the dew point. Every patch of air has a dew point. It's the temperature where the air becomes saturated. Can't hold any more moisture. If the air is humid, the dew point is high. It doesn't take much cooling to reach it. If the air is dry, the dew point is low. You need significant cooling before condensation starts. On clear nights, dew forms heavily. The ground can radiate heat directly to space with nothing blocking it. Surfaces cool below the dew point. Water appears. On cloudy nights, clouds trap some of that heat. They radiate it back down. The ground doesn't cool as much. Less dew forms. sometimes none at all. Dew forms best on surfaces that cool quickly. Grass is excellent. The blades are thin and exposed. They lose heat fast. Metal cools well too. Car roofs and hoods often have heavy dew in the morning. Wood cools slower and doesn't get as wet. Concrete holds heat and stays warmer longer. You'll see dew on grass before you see it on pavement. Spiderwebs become visible when dew forms. The droplets cling to the silk threads. Suddenly, these invisible structures light up with water. Each web becomes a constellation of tiny spheres catching the morning sun. The web was always there. The dew just reveals it. Plants use dew. In deserts and dry climates, dew can be a significant water source. Leaves absorb it. Roots take it from the ground. Some plants have evolved to maximize dew collection. Their leaves are shaped to funnel water toward the stem. Nature wastes nothing. Frost is frozen dew. On cold nights, when the surface temperature drops below freezing, water vapor condenses directly into ice crystals. No liquid phase, just air to solid in one step. This is called deposition. The ice forms in delicate patterns. Feathers, ferns, geometric designs that melt as soon as the sun hits them. Dew is proof that water moves constantly between air and ground. The atmosphere releases moisture every night, gives it back to the surface. Then the sun rises, warms everything, and the water evaporates back into air. The cycle never stops. Dew doesn't fall, it appears. Born from the air itself, when the world cools down and can no longer hold what it carried all day. Dew forms when air cools at the surface, but sometimes air heats up violently and rises with tremendous force. That's when you get thunderstorms. And if you watch a large storm from a distance, you'll notice something strange about its shape. The top spreads out flat, like an anvil. There's a reason for that. Thunderstorms build upward. Hot, humid air at the ground rises fast. As it climbs, it cools and moisture condenses. This releases heat, which makes the air rise even faster. It's a feedback loop. Rising air, condensing moisture, more heat, faster rising. The storm grows taller and taller. Some reach 40,000 feet, 7.5 miles high. But eventually, the rising air hits a limit. The boundary between the troposphere and the stratosphere. This boundary is called the tropopause. Below it, temperature drops as you go higher. Above it, temperature starts increasing again. That change in temperature creates a barrier. Rising air loses energy as it cools. But at the tropopause, the air above is warmer. Warmer air is lighter. It resists being pushed aside. The rising air can't punch through. It's like hitting a ceiling. The upward flow stops, but the air is still moving, still full of momentum. It can't go up anymore, so it spreads sideways. It flattens out across the tropopause, spreading in all directions from the central updraft. This creates the anvil shape, a tall column of storm with a wide, flat top. The anvil can extend for miles downwind. Sometimes it reaches 50 or 100 miles from the main storm. High altitude winds at the tropopause push the spreading cloud in one direction. The anvil points the way, the upper winds are blowing. Meteorologists use this to track wind patterns they can't see directly. Ice crystals fill the anvil. At that altitude, everything is frozen. These crystals are small and light. They stay suspended in the spreading air, creating a sheet of high cloud that can block the sun even when the main storm is far away. The anvil arrives before the rain does. It's a warning. Sometimes the updraft is so strong it overshoots the tropopause, punches through into the stratosphere. This creates a dome bulging up from the flat anvil top. It's called an overshooting top, a sign of an extremely powerful storm. These storms often produce large hail, damaging winds, or tornadoes. The overshooting top doesn't last long. Within minutes, it collapses back down. But while it's there, it marks the storm as dangerous. Not all storms form anvils. Small thunderstorms don't grow tall enough. They build up a few miles and then dissipate. Only large organized storms with powerful updrafts reach the tropopause. These are the storms that last for hours, that move across entire states, that produce severe weather. From below, you can't always see the anvil. You're too close. It's overhead, blocking your view. But from 30 or 40 miles away, the shape is obvious. A massive tower of dark cloud with a spreading flat crown. The signature of a mature thunderstorm. A storm that has reached its full height and is now spreading its power across the sky. The anvil is architecture created by atmosphere, a ceiling that won't break, air forced to spread instead of rise. The storm's ambition meeting the stratosphere's refusal, and the result is one of weather's most distinctive shapes, visible for miles, announcing power and presence across the horizon. Storms build upward until they hit the ceiling of the troposphere. But there's pressure everywhere, not just in storms. Right now, sitting still, you're experiencing tremendous force from the air around you. You just don't notice it because your body pushes back equally. Air has weight. Each molecule is tiny, but there are countless trillions of them stacked above you all the way to the edge of space. All that air pushes down. At sea level, this creates about 14 pounds of pressure per square inch. A square foot of your body has 144 square inches. That's over 2,000 pounds of pressure pressing on every square foot of you. Your body doesn't collapse because it pushes outward with the same force. The air inside your lungs, the fluids in your tissues, the pressure in your blood vessels, all of it balances the outside pressure. You exist in equilibrium. The air squeezes in, your body squeezes out. Neither wins, but when air pressure changes, you might feel it. Before a storm, pressure drops. Air rises into the developing system. Less air above you means less weight pressing down. The change is subtle, maybe a few %, but some people notice. Joints ache, headaches start, sinuses feel pressure. Your body is detecting the shift. Rising air pressure feels different. High pressure systems bring clear skies and calm weather. More air stacked above you, more weight. Some people feel relief when pressure rises after a storm passes. The physical change matches the mental sense of clearing weather. Barometers measure air pressure. Old ones used liquid mercury in a tube. Air pressure pushed down on mercury in a reservoir. That force pushed mercury up the tube. More pressure higher mercury. Less pressure, lower mercury. The height of the mercury column showed the pressure. Modern barometers use other methods, but they're measuring the same thing. The weight of air. Pressure changes with altitude fast. Climb a mountain and there's less air above you. Less weight, less pressure. This is why your ears pop. The air pressure inside your ear is trapped. Outside, pressure drops. The difference becomes uncomfortable. Your ear releases air to equalize. Pop. Same thing happens in airplanes as they climb. Cabin pressure drops slightly. Your ears adjust. Deep underwater, pressure increases dramatically. Water is much denser than air. Every 33 feet of depth adds another 14 pounds per square inch. Dive deep enough and the pressure becomes crushing. Submarines have thick steel hulls to resist it. Divers have to manage pressure carefully or risk injury. Air pressure affects boiling point. Water boils when its vapor pressure equals the surrounding air pressure. At sea level, that happens at 212 degrees. On a mountain, air pressure is lower. Water boils at a lower temperature. On Mount Everest, water boils at about 160 degrees. Not hot enough to cook food properly. Climbers need special equipment. Pressure is invisible force. You're swimming in it right now. An ocean of air pressing on you from all directions. 2,000 pounds per square foot. A car's worth of weight on your body. But distributed evenly, balanced by your internal pressure. You feel nothing until that balance shifts. Then your body knows. Pressure is always there, always pushing. A constant force you live in without noticing, until weather changes the weight of the sky above your head. Air pressure pushes down on the surface, but high above, air flows in fast, narrow bands that steer all our weather. These bands are called jet streams, rivers of wind racing through the upper atmosphere. And they're the reason storms move the way they do. Jet streams form where warm air meets cold air. The boundary between them creates a strong temperature gradient. Hot, tropical air to the south. Cold polar air to the north. These air masses don't mix easily. They push against each other. And along the boundary where they meet, wind speeds up dramatically. The main jet stream in each hemisphere flows from west to east. In the northern hemisphere, it typically sits between 30 and 60 degrees latitude, right over the United States, Europe, and Asia. It flows at altitudes between 30 and 40,000 feet, right where commercial jets fly. Airlines use it to save fuel and time when flying east. They avoid it when flying west because it slows them down. Wind speeds in the jet stream average around 100 miles per hour, but they can reach over 200, sometimes higher. These aren't gusts. This is sustained wind, a continuous blast of air moving at highway speeds or faster. Nothing on the ground comes close to this kind of persistent wind. The jet stream isn't straight. It meanders, curves north and south in waves. These waves are called Rossby waves. They form because of the temperature difference between equator and poles, combined with Earth's rotation. The waves move slowly eastward, but the air within them moves fast. When the jet stream dips south, it brings cold air down with it. Arctic air floods into lower latitudes. Temperatures drop. Snow can fall in places that rarely see it. When the jet stream bulges north, warm air flows up. Mild weather reaches far northern regions. The position of the jet stream determines what kind of weather you get. Weather systems ride along the jet stream like leaves in a current. Low-pressure systems form along its path. The fast-moving air above helps organize storms below. The jet stream guides them across continents. A storm system can travel from the Pacific to the Atlantic in just a few days, following the flow of the jet stream the entire way. Sometimes the jet stream gets stuck. The waves stop moving. A pattern locks in place for weeks. This is called a blocking pattern. When it happens, the same weather persists day after day. If the block puts you under a dip in the jet stream, you get prolonged cold and storms. If it puts you under a ridge, you get extended, warm, dry weather. Droughts and heat waves often happen during blocking patterns. Climate change is affecting the jet stream. The Arctic is warming faster than the rest of the planet. This reduces the temperature difference between polar and tropical air. A weaker gradient means a weaker, more meandering jet stream. Some scientists think this leads to more extreme weather. Deeper dips bringing severe cold, higher ridges bringing intense heat. The research is ongoing, but the connection seems real. The jet stream is invisible from the ground. You can't see it or feel it, but it's there. A river of air flowing above you, steering storms, shaping seasons, determining whether tomorrow brings sun or snow. Everything happening at the surface is influenced by this high-altitude wind you'll never directly experience. The sky has currents, and they control more than you realize. The jet stream follows patterns. So does air pressure. Temperature changes predictably with altitude. All of weather follows physical laws. Yet, we still can't forecast it perfectly. We can see a hurricane forming and track where it's going. But we can't tell you exactly which street will flood. Weather is organized chaos, and chaos is hard to predict. The problem is sensitivity. Small changes lead to big differences. This is what mathematicians call chaos theory. Weather is one of the classic examples. Two nearly identical starting conditions can produce completely different outcomes a week later. A tiny difference in temperature here causes a pressure change there, which shifts wind patterns, which redirects moisture, which changes where rain falls. The effects multiply. Meteorologists use computer models to forecast weather. These models divide the atmosphere into a three-dimensional grid. Each box in the grid gets values for temperature, pressure, humidity, wind. The computer calculates how those values change over time based on physics equations. It steps forward minute by minute, simulating the atmosphere's evolution. But the grid has limits. Each box might represent 10 miles across. Everything smaller than that gets averaged out. A thunderstorm forming in one part of the box doesn't show up individually. It becomes part of the box's average conditions. This is necessary because calculating every cubic foot of atmosphere would require impossible computing power. So models simplify. And simplification means losing information. Also, we don't know the current conditions perfectly. Weather stations are spread out. Satellites can see clouds, but not what's happening inside them. Measurements have uncertainty. A temperature reading might be off by a degree. A wind measurement might miss local variations. These tiny errors feed into the models, and chaos amplifies them. One-day forecasts are usually accurate. The atmosphere doesn't have time to deviate much from the predicted path. 3-day forecasts are pretty good. Most major patterns hold. 5-day forecasts are decent, but less reliable. Details get fuzzy. Beyond 7 days, confidence drops sharply. By 10 days out, forecasts become educated guesses. The chaos has taken over. This isn't because meteorologists are bad at their jobs. It's because the atmosphere is fundamentally unpredictable beyond a certain point. Even perfect measurements and unlimited computing power wouldn't help past about 2 weeks. The chaos is built into the system. Small uncertainties always exist, and they always grow. The butterfly effect is a metaphor for this. The idea that a butterfly flapping its wings in Brazil could eventually cause a tornado in Texas. It's not literally true. One butterfly doesn't matter, but the concept is real. Tiny perturbations in a chaotic system can have large downstream effects. Weather is that kind of system. Despite the limitations, forecasts have improved dramatically. 50 years ago, a 3-day forecast was about as accurate as a 5-day forecast is now. Better satellites, more data, faster computers, and improved understanding of atmospheric physics have all helped. But we've hit diminishing returns. Each improvement is harder than the last. We'll never predict weather perfectly. The chaos prevents it. But we keep trying, because even small improvements save lives. Knowing a hurricane will hit 12 hours earlier than predicted lets people evacuate. Knowing snow will be heavier than expected lets cities prepare. Forecasting is fighting chaos with math. Sometimes chaos wins, but we're learning to lose less often. Weather is chaos we try to predict. But here's something forecasts don't account for. You're part of the system, not separate from it. Every breath you take adds moisture to the air. Every bit of heat your body radiates warms the space around you. You're not just experiencing weather, you're creating it. One person doesn't make much difference, but billions of us together change things. Cities create their own weather patterns. Concrete and asphalt absorb heat during the day and release it at night. Buildings block wind and create turbulence. All that human activity, all those cars and air conditioners and factories, pump heat into the air. Cities are typically several degrees warmer than surrounding countryside. We call this the urban heat island effect. This extra heat changes precipitation patterns. Warm air rises over cities. It pulls in cooler air from the suburbs. This creates a circulation pattern. Sometimes it triggers thunderstorms. Rain falls more often downwind of major cities than it would if those cities didn't exist. We've altered the weather just by gathering together in one place. Forests do the same thing. Trees release water vapor through their leaves. This adds humidity to the air. Forests also cool the surface by providing shade. They're darker than bare ground, so they absorb more sunlight, but they use that energy for photosynthesis instead of just heating up. A forest creates its own microclimate. Cut down the forest, and the local weather changes. Temperature swings get larger, humidity drops, rain patterns shift, farms change weather too, irrigation adds moisture, crops transpire water into the air. Bare soil between planting seasons reflects more sunlight than vegetation would. Every change to the land surface is a change to weather at some scale. Usually small, local, but real. Your body is a tiny weather system. You breathe out warm, moist air. Your skin evaporates sweat. Your core temperature is 98.6 degrees, warmer than most air around you. Heat flows from your body constantly. Stand in a cold room and you can feel it. The air near you is warmer than the air across the room. You're a heat source, a moisture source, a small engine of atmospheric change. This is where we started, with the air you breathe, the air that's traveled everywhere and touched everything. Now you understand that the relationship goes both ways. The atmosphere touches you, but you touch it back. Every moment you're alive, you're exchanging water and heat with the world. You're part of the cycle we've been exploring. Weather isn't something happening to you. It's something you're participating in. The moisture in your breath will someday be part of a cloud. The heat from your body will rise and mix with air that might become wind. You're woven into it, connected to every process we've discussed. From the ice crystals in high clouds to the dew on morning grass. It's all one system, and you're not outside looking in. You're inside, part of it. If you've enjoyed this quiet journey through weather, please like and subscribe so we can explore more science together. Leave a comment about what relaxed you most tonight, and I hope these facts give you peaceful dreams. The atmosphere is still out there, moving and changing. But for now, you can let it be. Breathe slowly and drift off, knowing you're connected to something vast and beautiful. Good night.